having second unit on Introduction to Fracture Mechanics consists of the following subtopics like Introduction, Fracture Mechanics, Stress Intensity Vector, Crack Tip Plasticity, Fracture Toughness, and R-Car. Earlier videos have covered Introduction, Fracture Mechanics, and Stress Intensity Vector. Now we'll see Crack Tip Plasticity. So the crack tip stresses and displacement relations are derived based on purely elastic analysis, and they are valid only if the crack tip material behaves elastically. In reality, the stresses cannot become infinity at the crack tip. Therefore, plastic deformation at the tip of the crack structure is inevitable, since the material cannot withstand the high crack tip elastic stresses without yielding. Plastic deformation taking place at the tip keeps the stresses finite. As the stresses decay rapidly when one moves away from the crack tip to nominal stress value, plastic deformation is often confined to a region at the crack tip. The region of plastic deformation is usually referred to as plastic jaw enclave or plastic jaw. So, ahead of the crack tip, based on the elastic solution, one can see the stress distributions like this. And as stress at crack tip, it goes infinity. So asymptotically it goes infinity. So obviously, material cannot withstand anything more than ultimate strength. So in the process of any stresses going beyond yield stress, the material ahead of the crack tip will undergo plastic deformation. And the plastic plastic zone can be obtained by determining to which distance R star, which is dynamically changes as long as stresses are above yield stress, can be found out by substituting stresses at y equal to yield stress. So one can get a relationship between the plastic zone size with stress inspector K1, which is given in this equation. So what happens is basically the elastic solution, theoretical elastic solution showing the dotted line. And as stresses goes beyond yield stress, they will has to get self-equilibrium out of the crack tip. So the stresses beyond yield stress will get self-adjusted, and the plastic deformation will go ahead of the original plastic zone size. So crack tip plastic and displacement relations are derived based on purely elastic analysis, and they are valid only if the cracked material behaves elastically. Plastic deformation at the tip of the crack in structure is inevitable, so the material cannot withstand the high crack tip elastic stresses without yielding. In reality, yielding occurs and is not allowed in the shaded area. This compensated by extending the plastic zone to be larger than the RP. This region of plastic deformation is known as plastic enclave, and the plastic zone size depends on the state of stress ahead of the crack tip. So when stress is held at S max, we'll have monotonic plastic zone size, which is given by 2 Ri, and the plastic zone size Ry is given by 1 by 2 pi k sigma whole square. This is for plane stress, and for plane strain, it is 1/3 of the plastic strain that is obtained in plane stress. Now, when the external load is brought to zero, since there is already plastic deformation occurred ahead of the crack tip, and beyond around surrounding this plastic deformation, they are elastic. So during unloading, the elastic stresses will try to squeeze in the plastically deformed material to the extent that again it yields in compression. So it travels from plus yield stress to minus sigma y. And this is plastic deformation that occurs due to the compressor is known as cyclic plastic zone size. It is given by 1/4 of the plastic zone size created due to the monotonic in plane stress. That's why we get 1/8 pi. Again, the relationship between plane stress and plane strain is the strains at plane strain will be 1/3 of the plane stress. So cyclic plastic zone size also will become 1/3 of the cyclic plastic zone occur at the plane stress. So thank you.